Okay, for the final module of today, we are going to be looking at plots and all sort of visualization. Just give a very brief, it might not run for 45 minutes, I don't know yet, overview of the type of figures we can do. The package I'm going to be using is called StatsPlots. The other package for plotting is called Plots. StatsPlot is plots and other things related to specifically the visualization of statistical data. Most of the plotting ecosystems is based around plots in one way or another. But so we're just going to load StatsPlots for convenience because that's usually my go-to. It's a little bit heavier. It takes longer to build or pre-compile, but it's just lets you do other things. So that's what we're going to be using. The second is plot themes. Just so I can show you that we can actually change the way plots look, and it is a part of plots by default. So the first time you install these packages, they might take a while. The first time you load them, they will definitely take a while. The first time you make a plot, it will also take some time. It is something that is known in the Julia community as the time to first plot problem. Because it's like notably the longest experience of your lifetime is when you start up Julia, and the time up until you get the first plot is going to be longer than you expect. There's a number of reasons for that, not really worth thinking about because we can do anything to fix them. But just know that it's normal that the first plot takes some time to appear. So just to show you, we're going to just call the function called plot, which is the main interface in to our little plotting device. It is, as I said, going to take a while. If you're working within VS Code, it is going to open a new panel on the right that will have the plot. So it's pretty cool that you can see the code on the left, the terminal at the bottom, and then the plots on the right. It's very it's very well integrated. If you have used RStudio, that is basically the same logic. So the first time you call a plot function, remember that we discussed that in the first week, it's going to be pre-compiled, and that is going to be long. And then every subsequent time where you call the plot function, it is going to be faster. So the first time we do a plot, it's going to open something that is the unit square and that has no data in it. That's cool. Plots in Julia, like anything else, are thing that you can put into variables. So we could have a variable called myPlot, and myPlot, if we call it, is going to be a plot. Let's do a thing. Let's say we could use a function called x-axis, and you notice that it is ending with an exclamation mark. That means that it's going to be modifying something, and we could not put anything, and if we don't put anything, it's going to modify the plot that is currently active, but we can also be explicit. And then we are going to say we want the x-axis to go from -1 to 1, and we want it to be called the x-axis, because we're not very in a creative mood this morning. And so we know that we have modified the plot here, and it goes from -1 to 1. So the question in the chat is two packages are not installed, or can I import them? You go into the package mods, a documentation to which I have linked in someplace in Teams, I think, and you do add StatsPlots, and then plot sims, I think, is going to be installed. When you do that, it's going to take some time. Just that, like, they're already installed here, and then you can load them. But the mechanism to install these two packages are the same mechanism you use to install any package. And again, it's important that you go and read the documentation for the package management system in Julia. There's also a video tutorial I can send you on how to do that. Oh, anyway, it's going to take a little while. So one thing that is the reason I'm showing you this x-axis things first is that because the plots are objects that we can modify. And so we don't need to build the entire plot at once. we can build the plot piece by piece. And then when we can change the axis, and then we can change them again, and we could add a new data, and we can I don't think we can remove things from the plot anyway. So we can also do the y-axis of my plots, and we can have it go from y0 to 2 and call it y-axis. And so that is changing the dimension of the axis. For the moment, there is nothing in here, but we can do, we're not going to do anything. We are going to use a savefig function. And we're going to, that is going to create a file for with our plot. So we're going to do savefig of my plot, and it's going to be my empty plot.png, for example. So when we do that, it is going to create an empty plot for us, which is here. That's a file. So I'm just, before we even go into let's add data to this plot, I'm just going to show you a few different things. If you want to make figures that looks good at high resolution, then there are a few arguments that we can use. You could do like using DPI equals 600, and that makes the plot looks much bigger here. But it also means that when we save the plot here, it is going to be much nicer and in a much higher resolution. We could also change the size of the plot. Let's remove the DPI thing. The size, we could be like 200 by 200. We want a very small plot. I will have a very small plot. It's very, very small. And so we will end up with a very, very small file as well. So that's a thing that we can do. We can change the size of the plot. There's a number of different things we can do as well. Let's change the aspect ratio so that 1 unit on the y-axis is going to be the same as 1 unit on the x-axis. Yeah, that's because I've used the wrong keyword. Aspect ratio equals 1. And let's do 2.5 here. Right. And so now we have a plot where this dimension is 2, and it's equivalent to the same thing here, which is this dimension is 2 as well. That's important for some type of visualization, not so much for others, but it's a thing that we can do. Okay. So let's add some data. There are different comments that will result in a plot being produced. This plot, which is going to do lines. There is scatter, which is going to do points. I'll probably need to see heat map, which is going to make a heat map. There is also contour, and there are a few others. They're all documented in the documentation for plots. I just want to go through the very basics of making some plots. Okay, so let's go with our little logistic model. So we've seen that during the first or second week. I don't really remember. We're going to have a time series, which is going to be 0. And it's going to have 1,000 elements in it. And the first value is going to be 0. It's like 1 to minus 4. And then we are going to do for time in 2 to the length of time series. We should really be writing a function that would modify the time series array here, but it doesn't really matter. We need to define R and K, which are going to be 1.2, 1.0. Then the time series at time, it's going to be let's do that. Let's do nt equal time series time minus 1. It's nt plus nt times r times 1 minus nt over k. Okay, we have a simulation of the logistic model. We should have a, oh, what's, all right, R, yeah. Let me fix this very quickly. Okay. Let's see what time series look like. Okay, so it's good. So what we can do now is plot this thing. So if we do plot time series, we are going to see a plot that is going to be a line, and every point in this line is going to be one of the values of our model. And so of course we know that like 1,000 is way too long, so we're going to do maybe 80, right? That sounds good, 80. And plot that. Okay, let's do 50. 50 is good. Okay. And so what we have here is the first time point, and then the second and third and fourth and so on and so forth. And so that is a way of plotting the actual time series. So you might notice that it is starting at 1, right, on the x-axis here. So let's just try to make this plot a little bit nicer. So we're going to add one time step here because we want the first to really be t0. So instead of just giving the time series that goes from 1 to 51, I'm going to say I want you to go from 0 to the length of the time series minus 1. And so the syntax we're using here is plot of x and then y, right? And if we do that, it is going to give us a plot that starts at 0 and ends at 50. So that's a little bit better. So what we're going to do next is take the time to turn this figure into something that we would not be ashamed of putting in a report, for example. So let's decrease that a little bit to 21. Okay, so we go from 0 to 21. Okay, so what is missing from this figure? The first thing is, well, let's say I don't really like the axis. I'd like to go from maybe 0 to 50. Oh no, sorry, it's 20. No. 0 to 20. Okay, that's better. So the axes are they're not larger than the actual data that we are using. And maybe the y-axis can go from 0 to 1.4. That makes sense. And let's do 1.5. Good enough. Okay. So we have changed the axis so that it is now, I don't know, like respecting the boundaries of the system. It doesn't start before 0, it doesn't go lower than 0, and then it's having a little bit of leeway at the top here. One thing we should do is really annotate our time series with a logistic model. We can say that it's like year of growth, for example, and then the y-axis is population size. Okay, so now we're coming up with something that is a little bit more interesting to look at. It's something that looks like an actual figure. There are a number of different things we can do. And let's say, for example, we don't want the legend. So we could say legend equals false. And the legend has just disappeared. Honestly, that we don't want the legend to disappear, but we want it to be outside of the figure, so we could use one of the many, I think it's outer top right, yes. We can use one of the many keywords to specify the legend to have it outside of the plot. And then again, if you go look at the documentation for the plots package, I'll put a link to that in Teams. It's going to give you all of the possible keywords for all of the possible arguments, for which there are many. there's literally tables and tables of different arguments. So you can specify pretty much every aspect of your plot. So, okay, we've done our thing. The time is right. We have the right data. The legend is where we want it to be. And let's do lab equals, let's call that simulated data. So we know that it's, like a simulation that we've done. So another thing we can do is change the frame here. So instead of having just the 2 axes, we could go here and say frame equal, I think ticks is going to, no, ticks doesn't work. Box is going to work, right? And we have something that is entirely containing the graph. There are multiple arguments. You could use origin, you could use none, you could use 0 lines if you want. And again, it's documented. So that's good. Well, then we can realize that maybe we are using a line to represent the data, but the data we have are actually a discrete time process. And so let's not do a plot. Let's do a scatter. So the difference between plot and scatter is that instead of having a line, we are going to have the points. Just the points, right? And so that's sort of more faithfully representing the reality of the simulation we're doing, but it gets more difficult to read the fact that we have oscillations in the model. So what if we do, let's add a line style to that. No, that doesn't work. Let's do a plot and then add a marker to that. Right. So what we've done here is that we have a line, but then instead of having just a line, we say add a marker. And so the keyword argument M is just a shorthand for marker. So we could use marker if we want. Instead of having a plain line, because it's not really something that is in continuous time, we could use line style, which is abbreviated as LS, and say, well, I want like dash. And so we have the points, and we have the line that is dashed, and it's all reflected in the legend on the left. Let's go here and here. And so we have our little plot. Okay, so that's something that is starting to look like something we could put in a report. One other thing we can do is change the colors manually. So let's say we want to change the color. So we could do color equals. Let's find one that is purple. Why not? That is going to be changing the color for the plot, right? And so. But we can also let's do something awful. Let's change the color of the marker, put it as green, and then let's make a very bold marker. Yeah, that's awful. Okay, so the sort of thing that we can do here is that we can fine tune. That's not really tuning what we're doing, but anyway. We can fine-tune every element of the plot. So we can change the size of the markers, we can change the shape of the marker, we can change the color of the outside and inside, and the color of the line, and then the color of the style of the line, and all of that. Let's just pretend that never happened. That's much better. Another thing that Plot has as an ecosystem of packages is a series of themes. So there are a few that are optimized for things like color perception differences between people. So if you're like red, green colorblind, maybe that like we should anticipate the fact that about 10% of people perceive colors in a way that is not what we might expect. And so we can use color themes that are accessible to everyone, regardless of the way they perceive colors. So let's use this one, for example, and what it's going to do is come up with a series of colors by default. So the previous color used to be blue and now it's orange. And you might be thinking, well, it's not making a huge difference because there's a single color. That is a very valid point. And so let's plot a series of random numbers. Let's do float 64 and we'll do 10, 4. I did the other way around. I don't know. Right. So if we call the if we call our plot here with let's do MC equals M equals circle as well. If we call a plot after we have changed the theme of that, we are going to have a new color scheme. So let me just let's make a few attempts. So this one is changing just the color. There's one called bright, with changing the color, but also specifying different grids. For example, there is one called mute, and I think these three are the ones that are designed to be accessible in terms of the colors they use. I like this one. I'm not quite, I think it does the work. So that is something that you can do. If you don't, you can specify your own theme, but if you don't know, it's always better to use the default one that is accessible, that is. And then that is something that you don't need to make any conscious decision about which color do I pick. You just pick a color palette. The important point is that it's also going to let you do plots that are consistent in a way, so you're always going to be doing the same kind of you're always going to have the same colors for the same thing, and all of your plots are going to look the same. So if you want to go really deep into the fine-tuning of the behavior, you might not want to use a theme, and for some figures, that's all right. But for the report that you'll have to turn in, I'm not expecting you to spend hours and hours crafting like professional-grade visualization. I just want a plot that is readable, that has labels, and that has a legend, and where I can tell the colors apart. So that is that sort of covers the very basics. There's a plot package. It exists. You can put all sort of arguments in it. You can change the axis. You could save the figures, and you could use themes. I'd like to show you maybe one additional thing, which is called the heat map. And what a heat map does is plot a matrix, essentially. So let's do heat map, and then we're going to do, sorry, not this one, 5 by 10 random numbers. Yes, sure. Okay, so let's do a heat map with 50 random values arranged as a matrix and 5 by 10. So that is, let's say you have population densities of a space, right? And you might want to arrange them show them in this sort of layout, or you have geospatial layers, just to pick an example for things I'm doing at the moment. That's one thing that you can do. You can adjust all sort of arguments, so you can change the limits of the color palette. We want it to go from 0 to 1, for example. It's going to, okay, let's move the random values outside, define them only once, and then go here. Okay. If you do a heat map, you can also change the color palettes that you're using. I could use like magma, for example. So there's also a fairly extensive documentation about which are accessible and which are not. So don't use things like spectral. Sorry, spectral is bad. Spectral is not uniform in terms of how it encodes differences between colors. Use things like viridis or plasma, magma, cividis, and inferno, depending on how metal you feel on a scale from cividis to inferno, I guess. So that is the thing that you can do. One one situation in which the aspect ratio of a plot is particularly important is heat maps, right? Because in this situation, well, if we know that we're working on a landscape, for example, and we know that each patch is square, then we would like each patch to be square in the resulting figure. So using the aspect ratio here can be very, very important. I need to check if there is a spy function. No, there is no. There is a spy function. There is a spy function, which is a specific version of heat map for Boolean values, if I remember correctly. Yes, it's making a little dot at every point where you have a value. It doesn't really work when we have a small matrix, but if you have a very large matrix, then it's sort of useful to see if you have any sort of aggregation of data at some points, and you could do that for a very large matrix if you if you feel like. It might take a while to update. I don't know, it's not updating anyway. Anyway, so the spy function is here. So if you have let's say again, you have a landscape where you have the presence and absence of some species and you want to know what it looks like, then you could use spy, and that's going to give you a black and white map of where things are. So that's something that you could use to your own advantage for example, the first assignment. And what is interesting that all of these functions, they use the same sort of, they use the same syntax. So if we want to do frame equals none, we can. If we want to use the aspect ratio equal 1, we can as well. If we want to, aspect ratio is 1 by default with spy, I think. If we want to change the color, we can. So one thing that is interesting that with the plot package is that it gives you this interface to either just like drop in new data, use a sim, it's going to make a figure that is good enough, or you can go and tweak the behavior of all of these components yourself. Depending on what you want to do, or if you want to do more complex visualization, then you might be using one or the other. Another thing that you can do that's fairly clever, I think, is that you could plot a function. You could plot a function, and it is going to, by default, give you the -5 to 5 range. So if you want to say, well, what is that? What does the sine function looks like? And we're going to call it sine. We can do that. And as I said, we can modify a plot. And one of the ways through which we can modify a plot is that we can add another plot on top of it. So what does cosine look like? And cosine, well, we could do plot and then exclamation mark. So that means add this thing on top of the plot. And it's going to change both the plot and the legend. So now we have a new plot, which is here, and we have a new legend entry, which is here. And we could also use custom function if we want. What does 1 over x look like? So if we do that, we say, well, and then suddenly it's of course making the range of the plot explode, but we can set the y-axis to be what we want, and so we're going to set it to -1, 1. Okay, well, this one was a bad idea because it's not really pretty, but let's do this. 1, 1, 1. Okay, so just to show you another interesting capacity of this package, let's say that we want the frame to be going through the origin, which for the specific figure that we are making here is maybe a lot more meaningful than having a box. So we can see that one of these functions is crossing 0, 0 and the other is not. And so that, of course, is working with any function that you might define. So that is something that we will be using next week when we look at the visual identification of equilibrium points in biological systems. That the ability to visualize a function without needing to just generate a time series for this function or a series of outputs is something that is fairly useful. If you go look at the documentation of plots, you can also check like the number of samples you put into the function evaluation. You can check the range over which you are evaluating the function. Let's try to see what happens. And then you can, again, change all of these sort of behaviors. Yeah, let's do 1, 2, 5. So that's one of the things that you can do. And it's always very it's always very useful to have access to that, because when you are working with a function, one of the questions you're often asking is, what does it look like, right? And so if you want to know what it looks like, then you can just drop the name of the function in plot, maybe specify the range, the domain on which you want to plot it, and then it's going to give you the results. There's a little bit of a callback to one of the previous classes. Let's have a look at cost circle sin. And so if we're taking costs and then composite that into, we're taking the cosine of sine, and that is something that we can also do with our plot function. So really anything that returns a function is something that we could pass to the plots package, and that is going to give us a nice visualization. Let's just do one last example. So let's take the square root function. Let's do no legend. Let's do frame equal origin. Oh yeah, that's good. And there is a keyword we can use, which is fill. And fill is taking a bunch of arguments, but it's basically up until what point do you want to fill and what is the opacity with which you want to fill. So that's an interesting way of saying, well, I want to have the area under the curve highlighted, because I think that either makes sense or looks nice, or both, ideally. And then I want it to go up and to be going up until 0. We can do that with sine as well. And then we're only going to see the area under the curve. If you want to, well, let's say for some reason, have a sense of what is the integral of a function over a domain, and that's the area under the curve, and that is one of the ways that you can visualize that, which I think is really nice. And because you're adapting the transparency, then we can do the same thing with cos. We don't need these two. And then we're going to see like how much these two functions overlap, for example. So there's a lot of little keywords in plot. It's a very, very extensive package with dozens of functions, hundreds of keywords. Each of these keywords can take between 1 and 25 arguments. So I have been using that pretty much daily for a couple years, and I still keep the documentation open nearly at all times, because there's a lot of things you can do with it. But for most basic visualization, it's going to be just a matter of a couple of lines. And I think it's an important tool to have in your toolkit. Another, if you're more used to the ggplot2 style of graphics, there is a package which is called Gadfly, which is the one I use when I'm done pretending that I'm a modeler and pretend that I'm a data scientist, because it's meant to work with data frames. So if you have data frames and you want to do the sort of thing that you would do with ggplot, there is a package called Gadfly. It does that. It's also really nice, entirely different syntax, entirely different approach to data visualization. But that's another thing that exists. There is nothing that prevents you from using Gadfly with the sort of output that you will get, but a lot of the package that we will use for the modeling exercises are going to interact directly with plot. So if you run a simulation of ordinary differential equations, you can just drop that into Plot. It's going to show you the solution. If you want to do that in Gadfly, you have to extract something yourself. It's less automatic, but it's also doable. So that sort of concludes the introduction to plots that I wanted to show you. I'm going to put a link to the documentation on Teams so you can have a look at that. And I will get back to you with the template for the first report in the next couple of days. And that's the end of our stream, and I will show you next week. Bye, everyone.